We'll wait few minutes. Is Technion open nowadays? We'll wait.
Well, it's semi-open. The courses are by online, but the idea is that they are the teachers, the lecturers have to do the lectures in class. The class is empty, but there is a big whiteboard and so on. So they are supposed to do it in class.
Ah, okay.
So that it looks as much as possible as normal.
Mm-hmm.
But it's by Zoom, yeah.
Zoom.
Is it the same in your universities?
In our universities, same, I can say, because some of the faculties are doing the same way. But if some of the faculties are recording the classes using iPad and all, and using the whiteboard in iPad, I mean, in the software, and there and then uploading it. And some of the faculties are doing exactly the same way you are saying.
Children at school, they go to school?
No. They are all at home. They are using Zoom. They are Google Classroom, Zoom. They are doing it.
Yeah. That's one of the biggest problems. There are children that haven't been at school for, I don't know what, half a year or more.
Yes. Maybe we start now, Prashanjit?
Yes.
Okay, just a second. Let me just, yeah. Okay. So good afternoon, everyone. On behalf of the organizers, a very warm welcome to Professor Moshe Marcus and all the participants of webinar on PD and related areas. It's my great pleasure to introduce Professor Marcus from Technion, Israel. Professor Marcus obtained a doctorate under the guidance of Shamuel Agmon Technion in 1964. Some of his notable works jointly obtained with his co-authors includes works related to Hardy inequality, large solutions, the boundary trace of positive solutions of semilinear elliptic equations, the generalized boundary value problem, which we think are very fundamental works in this area. He has published more than 100 papers in very prestigious journals like AISP Analysis Nonlinear, Arc Rational Mechanalysis, Communications in Pure and Applied Mathematics, Journal of European Mathematical Society, etc. He was the Dean of the Mathematics Department of Technion from 1986 to 88. CMS, which is the Center for Mathematical Studies of Technion, have been founded during that period. I suggest students and young researchers to have a look at his excellent book, which is jointly written with Laurent Veron, Nonlinear Second Order Elliptic Equations Involving Measures, De Gruyter publisher. Today he will be speaking on boundary value problems for Schrodinger equations with Hardy type potentials. I hope you will enjoy the talk thoroughly. For the participants, we request you to keep your questions stored in Q&A box. Moshe, it is over to you now.
Okay. Shall I start? Thank you very much. Thank you for the presentation. Now, the subject that I'm going to talk about, equations of this form, minus LVU equals 0, where LV is an operator, Laplacian plus V. V is the potential. In general, we consider these problems in a bounded Lipschitz domain in Rn. Although most of the presentation today will be in smooth domains, simply in order to make the presentation more easier. Now, the potential is in this talk is always assumed to satisfy the following two conditions. A1, that Vx blows up at the boundary at most like the distance to the boundary to the power -2. See, delta x is the distance to the boundary, and Vx is less than or equal to, can be equal to, a constant times delta x to the power -2. The second condition, that A2, is a condition that guarantees, for instance, the existence of a ground state, the existence of a green function, and so on. Now, in the case of if V may change sign, then this condition will look a little bit more complicated. And for this reason, in order not to complicate the discussion, I will simply assume that V doesn't change sign. And please notice that A2 is needed only if V is positive. If V is negative, so we should assume that V does not change sign. If V is positive, we need this condition. If V is negative, that's not needed. Under these conditions, we can apply potential theoretical results, mainly of Ancona, from Annals of Mathematics 88. And here are the main his main results that we shall use. First of all, as I already mentioned, LV has a minimal positive eigenfunction. I denote it by phi sub V. This is the ground state. It has a green kernel, and this green kernel behaves in the same way near the boundary. It behaves in the same way as the ground state. And for this reason, since the green kernel behaves like this, it follows, it's easy to check, that if tau is a, let's say, positive radon measure on omega, GV tau like this, then if tau is in this space, m omega with weight phi v, this is the meaning. Tau in this space, it means tau is a measure finite on compact subsets of omega and satisfying this. So if tau is in this space, then GV tau, the green potential of tau, is finite at every point in omega. If not, then GV tau is identically infinity. So GV tau is either finite everywhere or infinity everywhere, and this depends on whether tau belongs to this space or not. Another result, LV has a Martin kernel, KV, which is normalized at some reference point x0 in omega. KV is characterized by the following: for every point y in delta omega, as a function of x, KV is positive, LV harmonic. That's to say it satisfies LV, KV with respect to x equals 0. And x, and again, as a function of x, it vanishes continuously on delta omega except the point y. On the boundary of the domain, it's 0 except at the point y. So this sounds very much like the Poisson kernel. But there is one huge difference. The Poisson kernel exists. The Poisson kernel is a kernel which at every point, say P, X, Y, will have the same properties, but at Y, the boundary data will be the Dirac measure at Y. Here we don't assume that, and it's not true that the Dirac measure, that the value is the Dirac measure at Y, that the boundary value is the Dirac measure at Y. In fact, it's quite possible that the boundary data is infinity or zero. So therefore, we have instead this normalization that kV is equal to 1 at a fixed reference point in omega. This is the big difference between the Martin kernel and the Poisson kernel. We have also, just as with the Poisson kernel, we have this representation. If U is positive LV harmonic, then it can be represented as in this form through a measure nu, positive measure nu on the boundary, positive and bounded measure. And this is our notation for this integral. As I mentioned, LV in general has no Poisson kernel, but if the Poisson kernel exists, then the relation between KV, the Martin kernel, and the Poisson kernel is just KV is just the Poisson kernel normalized at the point x0. That's the whole difference. So it's essentially up to a constant the same as the Poisson kernel when the Poisson kernel exists. As I say, in general, it does not exist. The final property that is extremely important is the boundary Harnack principle. We shall address it as BHP. Now, it's to describe it in a brief way. Suppose that P is a point on the boundary, U, V are positive LV harmonic in a neighborhood of this point P in a ball of radius R around P intersect omega. And in addition, suppose that both U and V vanish on the boundary intersect the ball. Then Ux over UA is similar to Vx over VA. This means that each is less than a constant times the other. Here A is simply the point opposite P on the boundary of the ball with radius half r. PA is in the direction of the interior normal at P. So A is like the point above P, and we have this relation. Now, this relation is, in a simple case, it's familiar to every student of PDE, because in the case of second order elliptic equations with nice enough coefficients in smooth domains, this is simply a consequence of the Hopf lemma. Of course, this is not the case in general. By the Hopf lemma, in this case, we would have that the behavior of U and V is like a constant times delta, the distance to the boundary. And therefore, we would have this relation. Of course, in general, the behavior of u and v is not like a constant times delta. In fact, not necessarily like a function of delta. Now, I have referred to all of these results on the basis of the work of Ancona from 1988, but it should be realized that there is a long history behind it. The Martin kernel has been defined and introduced already by Martin in 1941. And there is a notion of Martin boundary defined for Riemann manifolds, which in general is different from the Euclidean boundary. One of the results of Ancona was that under the condition mentioned, mainly condition A1, the boundary, the Martin boundary is identical to the Euclidean boundary, but this is not the situation in general. Boundary points, I should say, instead of boundary points, you have in the Martin boundary, you have boundary elements, which may consist of certain sets. Anyway, the result that I have mentioned before, the representation theorem, is a very special case of the Martin theory, which is true under the special assumptions that I mentioned at the beginning. In the case of the Laplacian, all of the results that I mentioned have been known already in the 60s or early 70s. And they are essentially found, for instance, this in the papers of Hunt and Whedon from 68 and 70. That's for the Laplacian. The boundary Harnack principle is also contained in the second of these papers for the Laplacian, as I say. And there were weaker previous results by Carlson at the beginning of the 60s. Now, all of these results that have been originally proved for the Laplacian have later been extended, and this was a long process which continued more or less until the end of the beginning of the 90s. It was extended gradually to general second-order elliptical equations in divergence form or in non-divergence form, under various assumptions on the coefficients, with or without a singular potential. But when a singular potential was allowed, it was always assumed that V is less than a constant times delta x, not to the power minus 2, but behaves a little better. Delta to the power minus 2 plus a positive epsilon, just a little bit better. Or more generally, that V delta is an integrable function. This is the assumption at the basis of what's called gauge theory. So all of this did not include the case where V behaves like 1 over delta square. This was the achievement of Ancona, that he extended the results up to the case that V may behave like 1 over delta square. Now, some simple cases, which are, however, which contain, however, all the essence of the story. For instance, potentials of this type. where delta F is not the distance to the boundary, but the distance to some subset, compact subset of the boundary. In this, for such potentials, the condition A2 is simply that mu is less than the Hardy constant relative to Vf, which is this. This is the Hardy constant relative to Vf. Now, it would be, of course, of great help to us if we could estimate precisely the ground state phi V. But this is known only in a few cases. In the case where F is a singleton, or this is perhaps the most interesting case when F is the entire boundary, or when F is a smooth k-dimensional manifold without boundary. As far as I know, these are the only cases where the ground, where we have an explicit estimate, two-sided estimate of the ground state. Of course, in this case, this simplifies the research of the problem, but in general, it's not available. Now, there was recent, as I said, the research of the potential theory aspects dates from the 60s. But recently, there was much research of nonlinear problems involving the operator L. That's to say, all of the papers that I'm mentioning discuss either the case delta plus mu over delta x square, mu a constant, or delta plus mu over absolute value of x square when 0 is in delta omega. There is, of course, also a lot of discussion of problems when V explodes at an isolated point in omega. This is the inverse square problem, which does not fall in the same category because it needs some different results. So you see, perhaps one of the first recent works was this one of Bandle, Moroz, and Reichel. Then, well, you see the list here. It's a very partial list, and you can easily find many more papers if you look at the references here. Okay. Now, a quick overview of the results that we'll be discussing in our lecture. Well, I'm already behind time. Okay, I already mentioned that the basic assumption on the measure tau in order to have so we assume that u is a positive function, locally integrable, therefore the distribution derivative exists. We assume that this distribution derivative we denote it by tau, and we assume that it's a Borel measure in this space, which means what's written here. For any such function, tau need not be positive. It can be positive, negative, or indeed even change sign. But u should be positive. For such functions, we can define a notion of boundary trace, which we call the LV boundary trace, and denote by TR trace V of u. The definition is based on the harmonic measure. If D is a compact subset of omega, and it's a Lipschitz, we denote by this notation the harmonic measure for LV with respect to a reference point x0 in D, which we can assume is the same reference point as before. Now, I don't have time to describe exactly what the definition of the harmonic measure, but there is really no need of it, because if we look at, I mean, we can understand very well what it is if we just observe that if D happens to be smooth, then this is nothing but the Poisson kernel of LV in D. ds is the surface measure on delta D. Please note, D is a compact subdomain of omega. Therefore, LV has no singularity in delta, and therefore it has a Poisson kernel in D. It does not have a Poisson kernel in omega generally. And there is no harmonic measure in omega, but there is a harmonic measure in every compact subset, compact subdomain of omega. And this is what we denote, how we denote it. And with this notation, we have the definition of boundary trace, which is simply that, as you see here, you take a Lipschitz exhaustion of omega. That means the dn are increasing and the union is omega. And then you look at the measure u is defined in is a Borel function, a positive Borel function in omega. So this integral is well defined for every h in C omega bar. And what you have here really is the limit in measure of u dwv dn. It's the limit in measure of this expression. This is what it means. If we had here, instead of d omega v, instead of the harmonic measure, we had ds, this would be what is called the limit in measure. This is the limit with respect to harmonic measure. And so, if such a measure nu exists, we say this is the boundary trace of u. In general, a function will not have a boundary trace. When it has, this is it. Okay, now, two basic properties of this boundary trace. If u is positive LV harmonic, in which case it can be represented by the representation theorem as the integral of kv xy d nu y, then the trace of u is simply this measure nu that appears in the representation theorem. This was expected, and this is what it turns out to be. If tau is a measure in this special space that I have already explained what it is, then GV tau, the green potential of tau, has a boundary trace. The boundary trace is zero, as one expects for the green potential. But it's zero in the sense of this convergence in measure. Well, here I'm trying to explain why this is reasonable, but I really don't have time for this. I'm already a little behind time, so I'll skip it. A simple consequence of the Riesz decomposition lemma and the two properties that I mentioned before is the following. Assume, as we always do, conditions A1, A2. If U is a positive function in L1 log, L minus LVU equals tau, and tau is in this good space, then U has an LV boundary trace. Every such function has a boundary trace. And it can be represented in this form. Indeed, you see, well, it's not, there is, I didn't explain what there is the compositional lemma, so I cannot go into details, but if tau is in this space, then the green potential exists. U minus GV tau is positive. This follows from the Riesz decomposition lemma. U minus GV tau is positive. And it is harmonic because LVU minus LVU is tau, and minus LVU of GV tau is tau, so tau cancels out. And KV nu is, of course, harmonic. So U minus GV tau is a positive harmonic function, and therefore it has a representation of this form. And according to the basic properties that I mentioned before, the LV trace of GV tau is 0, the LV trace of KV nu is nu, so it's exactly what's needed. Now, the main results. You see, with the definition, with the harmonic measure and this definition of boundary trace, we have formally these results, and they are really easy to prove. But the problem is that we know very little about the behavior of the harmonic measure on the boundary of the domains Dn as they approach omega. We don't know how they behave. And therefore, one might say it's a sort of good theoretic presentation, but if you want an actual estimate, you cannot simply use the harmonic measure simply because you don't know in general what it is and how it behaves as you approach the boundary. So our purpose is to replace the harmonic measure by a weight function which will allow us, which turns out to be the precise harmonic measure and gives us the precise, not the precise harmonic measure, but equivalent to the harmonic measure. We'll see this a little later. And with this weight function W, we can prove precise estimates. So first of all, observe W is given. It's the ground state of V divided by the ground state of the Laplacian. And this is the first result. The integral of a harmonic function times W is bounded above and below by a constant times the norm of nu. The norm of nu is simply the total variation of nu. The constants depend on bar A, which is in condition A1. They depend on omega. They depend on the rate of convergence here. But of course, they don't depend on the function. This is an estimate of LV harmonic functions. An estimate of green potentials, well, will have two parts in it. In the first part, we only assume A1 and A2, and we can estimate the weighted green potential, the integral of the weighted green potential. It can be estimated from below by phi v d tau. We know that this is finite because tau is in m omega, in m plus omega phi v. If we have an additional assumption, here we need an additional assumption, B2. Then we have also the estimate from above. This assumption looks complicated, but just to make things more concrete, in smooth domains, conditions B1, B2 hold, for instance, when V is positive and the ground state is less than a power of delta, a power greater than 1/2. And this implies that conditions B1, B2 hold for every subset, compact subset of delta omega, when V is gamma over the distance to F to the power 2, and gamma is less than 1/4. Then the conditions hold for every such compact subset F. So they are really quite general, at least in these cases. In Lipschitz domains, there is a more subtle consideration, but I'm not going to talk about Lipschitz domains in this talk. There simply isn't time for it. Okay. Now, with these two estimates, that's to say, of the harmonic, LV harmonic functions and LV green potential, we can now obtain the following. Let U be a positive LV superharmonic function. That means that if minus LVU is equal to tau, tau is positive. Now, automatically, in this case, you don't have to assume that tau is in the good space. For superharmonic functions, it can be shown that it's always in the good space. Therefore, the LV trace always exists for superharmonic function. And according to the proposition that I mentioned before, U is equal to GV tau plus KV nu. And by the estimates of the KV nu and GV tau that I mentioned before, we have this estimate for the superharmonic function. It's bounded above and below by the norm of nu, and you might say the norm of tau in this space, m omega fv. This is the norm of tau in this space. So these are precise estimates from above and from below the same expression except for a constant. If U is positive but LV superharmonic, now I shall denote LVU equal tau. Note the difference. Here I put minus LVU equal tau. Here I put LVU equal tau. And in this case, tau is again positive. If I would have written minus LVU equal tau, tau would have been negative. So, in general, the LV trace does not exist. It exists if and only if tau is in the good space. And if this condition, that tau is in this space, if this condition holds, then we know that the trace exists. We denote the trace by nu. We have this relation, u plus gv tau equal kv nu. And in this case, both the weighted norm of u and the norm of phi v, the sum of them, of these two, is bounded above and below by the norm of mu. But the important point is that we don't necessarily have, for subharmonic function, there may not exist a trace. Actually, the case when a trace, in the sense that we define, doesn't exist, is the case of great interest. In that case, we can still define a trace, which will be a generalized trace, which is not a bounded measure, but an unbounded measure. And that makes the story much more complicated and also interesting. But this time, I'm not talking about that case. The main tools that are used in the study that I described are the potential theoretic results, which I listed at the beginning, and estimates of the Green and Martin kernel that have recently appeared in this journal. All of these results are valid in bounded Lipschitz domains for operators LV with signed potential satisfying A1 and the variant of A2, which I didn't want to spend time describing. That's why the present lecture assumes that V is, that the potential V has a fixed sign, doesn't change sign. And for simplicity, we also look, present things in smooth domains. In Lipschitz domains, the presentation, the results remain true, but I mean, all these estimates remain true, but the proof is much more technical. Okay, so we assume that omega is of class C2, the potential V does not change sign, and we have the following notation. dB is the set of points which are a distance greater, d beta is the set of points whose distance to the boundary is greater than beta. Omega beta, as you see, it's the distance less than beta. Sigma beta is the boundary of omega beta. And the following facts are known. The function delta of x, the distance to the boundary, is a C2 function in some neighborhood of the boundary, omega beta 0. That's to say, as long as the distance to the boundary is smaller than some number, beta 0. In addition, if we choose beta 0 appropriately, it's if every point x in omega beta 0, for every such x, there exists a unique boundary point that I denote by sigma x, which is the nearest to x. In general, this is not the case. You may have a finite number of points that are nearest to x, or even hold the boundary, but no, in a small neighborhood of the boundary, when omega is of class C2, then this is true. In Lipschitz domains, this is not true, even if you are near the boundary. Now, these facts allow us to introduce a set of coordinates that are called flow coordinates, and they are coordinates that exist in this boundary strip omega beta 0. And this is the definition. For every x, pi of x is delta x sigma x. Now this mapping is 1-to-1, and both pi and pi minus 1, its inverse, are in C1. That's because although delta is a C2 function, sigma is only a C1 function, unless we assume that the domain is more smooth than C2. If it's C3, then I can say that these are in C2, if the boundary is C3. Okay, so we have a nice set of coordinates in a boundary strip of width beta 0. Now, this is just a notation to simplify some. When I say F is similar to G and denoted like this means simply that you have such a thing. I should have said not real function, but positive functions. Then F similar to G in a set E means this, and the constants are called similarity constants. Okay. I have already stated this before. The estimate for the LV harmonic functions, positive LV harmonic functions. I just want to give an idea of the proof, provided that I have time, and perhaps I have a little time for that. We'll see, we'll try to do it quite fast. We denote by a sketch of the proof. Let's denote by ny, the inner normal at y, and by cy, a cone vertex y completely contained in omega, and we choose this m, I mean the opening of the cone, in such a way that copies of the same cone can be fitted to every point y on delta omega. So all the cones cy are copies of the same cone. Now, it is known that if you take the product of kv and gv, you see, this is kv relative to the pole of kv is the point y on delta omega. For gv, you have here the reference point x0, and you now look at kv and gv along the normal which enters from y into omega. When it doesn't go too far, t is between 0 and half beta 0. Beta 0, we mentioned it before. So it is known that this product behaves like along this normal behaves like t to the power 2 minus n. You can look at the case of the Laplacian and it's immediately clear. But in general, it's quite a deep result. The similarity constant here is independent of y. Now, if you have this relation along the normal at y, then by the strong Harmonic inequality, this relation remains true not only along the normal, but also in the entire cone Cy, of course with other constants, but in the entire cone Cy. And so you have, for instance, here you see that, okay, you have KVGV behaves like that. K0 times G0 also behaves like this. Therefore, you have that K0 times G0 behaves like KV times GV, except that I wrote it as like this. And GV behaves like the ground state, G0 behaves like the ground state of the Laplacian. So you have this relation, not only on the normal, but in the entire cone. And then you see that KV times phi v over phi 0 is similar to K0. Take KV here, and you see that it's similar to K0. You have this thing in the cone, always with constants, similarity constants independent of y or of beta. So we have this relation. Well, if we have this relation, we know what happens when this tends to 0, when beta tends to 0, this simply converges to some constant, which depends on the opening of the cone. But since we assume that all the cones are similar to the same cone, to one single cone, the constant will be independent of y. And therefore, we have that this, when beta is between beta 0 over 2 and beta 0, is bounded by above and below by a constant that is independent of y or beta. Now, by this happens in the cone Cy, but we should know also what happens outside the cone Cy. So outside the cone, by BHP, the boundary Harmonic principle, KV and GV behave in the same way, because KV is an LV harmonic and vanishes outside, on the boundary outside Y. So you have that KV is simply similar to GV, that's to say, its KV is less than a constant GV, greater than a constant GV. Therefore, B1 implies that if you look outside the cone, on sigma beta, on this surface, which is the boundary of omega beta, but outside this cone, you can replace GV, you can replace, KV by GV, and GV, of course, behaves like the ground state. So this integral is essentially phi v squared over phi 0. And by assumption B1, this tends to 0. So if you put this together with the behavior inside the cone, you get that this entire integral on the surface sigma beta, which is the surface at distance beta from the boundary, is the same, like behaves in the same way like the integral of k0. K0 is for the Laplacian on the same surface. And this we know converges to a constant. So therefore, this will converge to a constant, and the constant is independent of y. And so we have the result that we stated here for the special case where nu is just the Dirac measure at y. When nu is the Dirac measure at y, this is kvxy. And what we proved is this result when you have here kvxy. And how do you get the general result? Simply by Fubini. It's a trivial thing. By Fubini, once you know the result for each y, you get the full result for nu. This is the idea of the proof. Now, well, I think I have to finish now, which is very unfortunate. I'll just mention one more important result, an estimate of the LV harmonic measure. Now, estimates of LV harmonic measures have been dealt with in the past very often, but only for second-order elliptic equations without singularity, without a singular potential, or a singular potential not with the strong singularity, 1 over delta square, but a more mild singularity. I believe that this is the first time that one, anyway, I'm not aware of any previous estimates of the LV harmonic measure when V has the strong singularity. And this is the estimate that we obtain. If you take we are on this surface sigma beta, we take the integral of sigma beta over over the integration of the cone with sigma beta, which is just a small ball, n-1 dimensional ball. And we find that the integral of the harmonic measure on this small neighborhood of the point is equivalent to the value of W at this point. Well, I intended to give the idea of the proof, but of course we shall have to skip all this. I want to mention that with the results that we have already seen, in particular this result about the estimate of the harmonic measure, we can prove that we already know that GV tau d omega v tends to 0, the integral. We can now prove that the same is true if we look at the integral of GV tau ds with weight W, then the same result is true. So essentially, W ds represents the harmonic measure. Well, I have to skip all of this because it's late. Applications to semi-linear equations are very much known from the papers that I mentioned before, except that in those papers, this equation was considered only for V, which is mu over delta square or mu over absolute value of x squared, but not more general V. Now, here we can deal with any V, as I mentioned, as I mentioned before, and we can get all the usual results. For instance, U is a solution of the equation, a positive solution of the equation, if and only if FU phi V is finite. For FU, you can imagine that you have a power of U, like U to the power P, and U is positive. And you have a sufficient condition for the existence of a solution to this boundary value problem. And the solution under this condition, it's a sufficient condition, the solution existent is unique. In the special case where nu is delta y, the Dirac measure, then this condition is necessary and sufficient. In general, it's only sufficient, but for this, it's necessary and sufficient. And of course, you have an a priori estimate for solutions, because indeed a solution of this equation is simply a subsolution of LVU equals 0, and you have this estimate. Okay, thank you for your attention.
Thank you very much, Moshe, for such a wonderful talk. Now I will request the participants to put your comments or question in the Q&A box, if you have any. So let me see.
Comment on what? I couldn't understand.
I said the participants, the attendees, if they have any comments or questions, to put in the Q&A box, so that we can address you can address the questions.
If you have questions.
I mean, I said this to the participants.
Okay, fine. Sure.
Yeah, if they have questions, to write it on the Q&A box, so that we can. I mean, you can address the questions. That's what I said.
All right, very well.
So meanwhile, I have a question. As you mentioned towards the end of your talk, that since now we have this machinery, so one can have this semilinear problem with the absorption terms. So those results, that's been already done, or it's just I mean, with the general one, just last few slides of the semilinear.
Most of what I described here, yeah, it's in a paper which for the time being it's in archive. I put it there a couple of months ago. I don't remember exactly, but what is beyond this, the same results in Lipschitz domains. This is almost finished, but it's not yet it's not yet completely written. It's only partly written for Lipschitz, the extension to Lipschitz domains. There are also many important consequences of the estimate of the estimate of the harmonic measure, which I'm going to describe in this paper that is being now prepared. So there is what I actually presented here really is already in a paper on archive.
Okay, and also the equation with the source terms, have that been studied?
What? Which equation?
Morse term. So you mentioned the absorption nonlinearity, right? With the
Source
source nonlinearity.
Well, first of all, the general theory will apply to equations with source term. Obviously, in this case, the solution would be a super solution of LVU equals 0. You always have a boundary trace and so on. But there, of course, the main question is the existence of solutions. Here, too, I didn't have time to talk about this, but it's not that for every measure nu there is a solution. To get, even in the absorption case, you need certain condition on the boundary trace in order to have a solution. And there are sufficient conditions which can be expressed via certain capacities. And yeah, they will appear. Everything is not, it's not yet, it's not yet written. In the case of source term, one will have to look at the size of the norm of nu. Perhaps the result will give us existence for sufficiently small norm, but I didn't look at that yet.
Okay, I think there is a question here in the question answer box. So the question is from Fuktai Niguin. So Tai has written, thank you Moshe for an interesting talk. When trace V equal to delta V, just a second, trace V equal to delta Y, that is the Dirac measure at Y with Y in the boundary, do we know the behavior near Y of the solution U to the semilinear equations?
Of the what? Of the nonlinear equation?
I think if you want to read it by yourself, you can also click Q&A box if you like to read it.
I'm
Do you
sorry,
see
is
Q&A
it
box?
possible to see because my hearing is not very good. Is it possible to see this thing?
Yes, yes. Can you see Q&A on the bottom of your screen? Right side on the bottom Q&A box?
The bottom? No, it's on the top, perhaps. Yeah, I see here. I see there are some question and answer. So,
yes.
Okay, so which one do you mean now?
Tai, I mean, Tai has asked a question.
Okay, one is by, I see, Nguyen, Fuktai Nguyen. When trace V is delta Y. The Dirac measure with Y in partial. Do we know the behavior near Y of the solution U to semilinear equation? Answer, yes, we know it. But what does it mean? We know that it behaves like KV.
Hello, Moshe.
Yeah.
I would like to know, like, do the solution behave exactly like the Martin kernel when X
That's what I'm
tends
saying. It behaves like KV, yes, non-tangentially.
Non-tangentially. Okay.
Of course.
Yeah.
Differently. Yes.
Okay.
In fact, many of the results that you and I obtained in a special case can be extended. Most of them can be extended without any essential change in the proof to this more general case with more general potentials. But this is not necessarily the most interesting part. The most interesting part, to me at least, is the characterization, for instance, the characterization of measures for which solutions exist and so on. But yes, we know the precise behavior.
Okay, thank you very much, Moshe.
Fine.
Yeah.
Now there is another question by Osborne. How might your results be extended to equation given by replacing the Laplacian by divergent form second order operator with bounded coefficients? Well, essentially, I think that most of the basic results do extend to this situation. In fact, the way that they extend is by estimating the relation between the harmonic measure in the case of the Laplace operator with the harmonic measure in the case of the general second order equation. Of course, I mean not the linear equation, but of the equation plus V, and that those estimates can be obtained for under very general conditions on the coefficients. This is something that I said there are many consequences of the estimate that already exists for the harmonic measure, and I'm going to write them in detail. In fact, they are in the process. Okay, there is something by, I don't know, there is something where there is no question, and
I have one more question.
There is something back. Okay, I suppose these are the only questions.
Moshe, I have one more question. Hello?
I don't see.
Yeah, I have a question. I have a question.
Yeah, I'm listening.
Yeah, so any regularity results is known for equation, if we just consider linear equation, I mean, with this operator, Schrodinger operator that you said, so any regularity results are known?
Regularity in which sense? I mean, what we know is, for instance, how solutions behave when at a portion of the boundary where they vanish, in the sense that the trace, the LV trace vanishes, then we can say what's the behavior of the solution. We have, of course, the estimates along the surfaces sigma beta, which tend to the boundary. So this will tell us something about the behavior of the solution at the boundary, because we have exactly how the integral of, say, the weighted integral of the solution U on sigma beta, how it behaves as it approaches the boundary. So this will, of course, give us, for instance, this retrieves most of the results that have been proved for the case of V equals mu over delta square, and there you have the precise approximate behavior, but you have the behavior in terms of the ground state, and there you know how the ground state works, so you know exactly you can tell exactly the behavior of the solutions as well. In general, you don't know how the ground state behaves, And it's an interesting, there is a whole series of problems which are of interest. For instance, in special cases, when the domain F on the boundary, not the domain, the set F on the boundary is really the closure of an open set with smooth boundary relative to the surface sigma beta, let's say, to the relative to delta omega. In those cases, although you don't have the exact behavior of KV, you know enough to be able to give good estimates. But it requires work. It's not, they are not written. It's something that it's worth working on. Yeah. So.
Okay. Okay. Okay, then thank you. Thank you very much, Moshe, once again. So for making this session successful, we hope to get your participation in future talks as well. And we'll meet for the participants. There is an announcement that we will meet on next Tuesday for the talk of Professor Xavier Rossathan on the Neumann problem for the fractional Laplacian. Now I request all the participants to leave the platform. Thank you very much. Thank you, Moshe.
Thank you, Moshe. Thank you. All the best.
Bye-bye. See you.